Well, I will. I'll begin with a word of prayer. Ahem. Hem. 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 Dear Father, we thank you for this day. I thank you for these students and just ask that you just bless this class, Lord. In your name I pray. Amen. Well, I have no idea how you guys did on the test because I have not started grading it. So, but I will soon. Don't feel any pressure to just. I thought I would give you all a.
We can just do a repeat of the count 2 minutes.
Just give you guys all a 70%. You know.
If someone were to see happens in your life,
Like the. Is it the Green Party? Is it the Socialist Party? They got some new manifesto for the government should support those who are either how's it go? Either unable or unwilling to work. So you do that like for classes, but unable or unwilling to study, you know. I'm just kidding. You guys are all A students. Well, I don't know. I assume you're all A students until I grade. Okay, that's not true. I graded your quiz. So from an actuarial perspective, well, you know, quizzes are to improve, right? So let's hope the test is better than the quiz. So vector spaces. I prefer reality to encouragement. Let's see here. So a vector space, so this is definition. A vector space V over a field F. The notation for this would be, say, V of F sometimes is used to denote this, all right, is a set V together two functions, and those functions are plus, which is a mapping from V cross V back to V again. And also scalar multiplication, which I use a dot for. Scalar multiplication goes from the field cross the vector space back to the vector space again. So the typical notation for these maps is just, you know, x, y maps to x plus y. This is vector addition. Or c times x, c comma x maps to c dot x. So this is vector addition. And this is scalar multiplication. That's what we call these maps, provided they fit the terms and conditions. So what are the terms and conditions for this being an honest-to-goodness vector addition and corresponding scalar multiplication? Well, if they are those, first of all, they're functions, and second of all, they satisfy this list of 10 axioms. And these axioms, and this is not a logically minimal set of axioms I'm about to write, okay? So A1, x plus y equals to y plus x. A2, x plus y plus z makes sense. No matter where you put the parentheses, that's what? All right, so the first one is what? Axiom 1 is the vector addition commutes. Axiom 2 is vector addition is associative. Axiom 3 would be that there exists 0 in V such that x plus 0 equals to x equals to 0 plus x, all right, for all x in V. In other words, axiom 3 is that there exists an additive identity, a zero vector, as we call it. Axiom 4 says for each x in V, there exists minus x in V such that what? Such that x plus minus x equals to 0. So every vector has a a negation. There's a negative vector for each vector such that when you add the negation of the vector to itself, you get back to the 0 vector. This is axiom 4. All right, so these first 4 axioms, if you want me to give you a sort of a bird's eye view of these, what these say is that V is an abelian group with respect to vector addition. So if you were studying group theory, like you will in the next course, Math 421, you know, those, just that stuff alone gives you an abelian group, all right? But it goes on. Then there's axiom, I'll put it over here, axiom 5. Axiom 5 is that 1 times x is equal to x for all x in V. And here 1 is in the field. Axiom 6. Axiom 6 says that if we take AB scalar multiplied by x, it's the same as multiplying by B first and then multiplying by A. So this is for scalars A, B, and x a vector. By the way, we call the numbers that are multiplying scalars. All right, so like A and B here are scalars. C in the original thing here, this is a scalar. Axiom 7 says that says that A scalar multiplied by x plus y is A times x plus A times y. Axiom 8 says that if we have a sum of scalars, A plus B, and it multiplies by x, we get A times x plus B times x. Axiom 9, actually axioms 9 and 10 are redundant, but I state them again for emphasis. So axiom 9 says that for each pair x, y in V, the x plus y is single vector. And this axiom 10 is for each c in the field and x in the vector space, the scalar multiple of x by c is a single vector. So can you guys tell me why I'm saying that axioms 9 and 10 are redundant? Where have I already implicitly said that? Yes. See, right, the two operations mapping V cross V and F cross V to V, because I said right here, I said they were functions, right? And you guys remember from Calculus 1, like day 1, Dr. Sprano, some of you, what's a function? It maps every element in the domain to a single element, right? Although that sometimes makes you think it's saying he's seeing the function's constant, but you got to find the wording for yourself that makes it clear to you. But each input has a single output for that input, right? I mean, anyway, so in that sense, axioms 9 and 10 are redundant. And in fact, if you're a minimalist, you could call this definition to a more minimal definition. I state the definition in this way, not because it's logically minimal, but for pedagogical clarity. Like, these are the things which make a vector space in a nutshell, all right? I mean, this is the definition. So now that we have the definition, and that's, by the way, why I had to have this, my computer open, because without the without my laptop open, I can never remember the numbering that I put in my notes, right? But once you have this, you can use this to prove things like Theorem 6.1.13. What's it say? It says if you have a vector space, right, over field F, we have the following results. First of all, result number 1, 0 times x is 0. Result number 2 here, c times 0 is equal to 0. And tell you what I'm going to do here, and I don't always do this, but for the purposes of communicating more clearly what's going on here, I'm going to put a vector on the 0 vector, all right? So one of these is not the 0 vector. It's in number 1. That's the 0 scalar, okay? There's a difference. Point 3 here, but generally speaking, we don't put vectors on vectors in here. Minus 1, scalar multiplied by x is equal to minus x. And 4, if cx is equal to 0, then either, well, let's say this, then x, then, how can I say this? Well, then c is equal to 0 or x is equal to 0. At least one or, and I mean mathematical, or right? I mean, like, they could both be 0, but at least one of them has to be 0, right? So those are derived consequences from these axioms, all right? And we could look at page 116 in the notes. I go blow by blow, proving 1, 2, 3, and 4 from the axioms, all right? And if we have time today, we'll get back into that. But if we don't, you can look at that yourself on page 116. The point is, we are going to, page 116. Yeah, page 116. The point is, we will use these going forward, all right, without reference. Like, I'm never going to say, oh, by theorem 6.1.13, these things are true. So we just accept that these are true going forward, all right? If we're in the context of a vector space, we have these things to work with. Yeah. Oh, no. There is nothing about multiplicative inverses here. No. Mm-mm. What you mean, like vector multiplication or scalar multiplication?
Scalar. I mean, there's usually, when you list out the additive inverse,
Well, that's a good question. So the vector space is a group with respect to vector addition in the sense that there's an inversion with respect to addition. But scalar multiplication, it's not that kind of thing. I mean, we're not multiplying the two objects of the same type with scalar multiplication. We're multiplying like a scalar times a vector. Those could be different things. So it wouldn't make sense to say like the inverse. Now, in the context that your vector space was the same as your set of scalars, in that context, multiplicative inverse would make sense, could make sense. But generally speaking, we don't have a way of dividing by a vector, not usually. If you can divide by a vector, that's a fairly special thing. More on that later. But so let's look at some examples then. So each one of these examples will, satisfy all these axioms. So example number 1 for me is always just V equals to, well, let's say Rn with, the field. My choice of field here is the reals. Just the usual column vectors forms a vector space, right? Where x plus y, the jth component of that is by definition x sub j plus y sub j for all j, right? And what's the definition of scalar multiplication? Well, c times x, the jth component of that, is c times x sub j, right? And so that's vector addition, that's scalar multiplication in Rn, and those rules satisfy all the axioms. In fact, that example motivates this definition. Right? That's why we make vector space what we do. Now you could be greedier, right? Like this is a real vector space, right? So 2, you could make v equal to Cn just the same, right? You could use complex numbers. And then this would be what's called, you could put the field being a complex, you use the complex scalars, right? This would be a complex vector space. All right, the definition of vector addition and scalar multiplication, same song and dance. You know, I'll just say any field, right, makes the Cartesian product with the field in itself n-fold times an F vector space. All right? So Fn for any field. I mean, we could do Z7, triples of, residue classes mod 7. This would form a vector space over Z7. But I want to talk about example 2 a little bit more, because there's something that happens when, let's talk about 2 some more, but it's going to be example 4 here. So a given set may have more than one possible vector space structure. So let me just take a step back here. Instead of talking about Cn, let me just talk about C itself, all right? The complex numbers, right? This is things of the form a plus ib, such that a and b are real numbers, right? So yes, I mean, that is a complex vector space. We could look at it that way, but we could also look at this as a real vector space. What do I mean by that? We can look at the field of scalars as being the reals. See, because if I take a real constant a times x plus iy, what do I get? Yeah, ax plus iay, right? Which is, again, a complex number. So multiplying a complex number by a real number gives me back a complex number, and if you check it, all the axioms for the vector space are satisfied. We can multiply by a real scalar. So this is just like a general comment. All right. If, we have a complex vector space, so you could say v comma c if you like. This would be an alternative notation which might be helpful, right? We can treat the same set V as real vector space by simply what? Restricting the C scalar multiplication to real scalars. These are different vector spaces. As we go on this semester, we'll see they have quite different structure. All right? For example, they'll have different dimension with respect to the structure here. Now, another example we could give would be the v is equal to the reals over the reals. So take my field to be the reals. I could do that. This is a vector space. I mean, it's a stupid thing, but you can check the axioms are satisfied for the real numbers. But here's the thing. You could also restrict the scalars to what? What field is, what's a subfield of the reals? Right. Could restrict scalars from R to Q. All right. Then R over Q is a so-called rational vector space. Actually, I'm not sure about that terminology, but that's not the typical terminology I would hear would be the reals are a vector space over the rationals. Okay, the reals are a vector space over the rationals would be what we usually say. Or you could say this is a Q vector space. Again, these are really, really different. The real numbers over the reals are one-dimensional once we make sense of whatever that word means, okay? In contrast, the reals over the rational numbers are infinite dimensional. So the vector space structure is really different between these. Your choice of scalars is a lot of the story. Right, enough about this weirdness. Let's go on to other examples. What else can we do addition and scalar multiplication for? How about take any field. Look at m by n matrices, right? Over the same field. So if we have A plus B ij, by definition, Aij plus Bij, right? C times A, ij is C times Aij, right? So these define matrix addition and scalar multiplication, and guess what? Those terminologies are not at odds with the usage I'm adopting today. In fact, the set of matrices, again, forms a vector space with respect to the standard notion of matrix addition and scalar multiplication. All right? So 2 by 2 matrices, 3 by 3 matrices, 3 by 4, whatever. There's infinitely many examples of these. All right? What else could you do? Let S be a, well, let's just keep it interesting, non-empty set. All right? Let V be a vector space over a field F. Then, here's my notation. If we look at F from S to V, let's call this W. And what this is going to be is functions, little f, going from the set S to the vector space V. All right? So vector space valued functions from some set. That vector space could be any of the previous examples. or ones we haven't talked about yet, all right? This forms a vector space. What's the vector addition and scalar multiplication here? So if f and g are in W, and c is a scalar, we define f plus g of x equals, this is the definition, f of x plus g of x. So the old function f, the old function g makes the new function f plus g defined by pointwise addition. This makes sense because the addition on the right-hand side is happening in the vector space W, where vector addition is defined and single-valued, which means that f plus g is also a function if f and g are functions. Also, you can tell me c times f is what? Cf of x, right? So these are definite, these define W over the field F. I mean, these give W a F vector space structure. This is a blindingly general example, right? I said S could be any set, right? What's an interesting example is when we take S and V both equal to the reals, right? If we look at the function space from the reals to the reals, that's often an interesting case. So real valued functions of a real variable, right? That's a vector space. The sum of two real valued functions of a real variable is a real valued function of a real variable. Scalar multiple, again, same thing. So these are my main examples. There are more. Oh, I guess the other example I should mention before I forget, polynomials. And so those would be things of the form. So polynomials, we, notation here, f bracket x is the set of like some, let's say j equals 0 to infinity of c sub j x to the power j such that cj is in the field for all j and only finitely many Cj non-zero. This is polynomials over the field F. This is also forming a vector space. How do you add two polynomials? You just add the corresponding coefficients. How do you scalar multiply a polynomial? You just scalar multiply each coefficient in the thing, just like we usually do. Again, a vector space. All right? Okay. So many examples, right? So many examples. So that brings us to, the next section, which is, I mean, up till now, you probably have the feeling like, how on earth can you ever really, I mean, if you're worried about a test in the future, like, how do you test on this? Like, I don't know, maybe not directly, but this is the language which you're going to be immersed in, right? So but the next section has honest to goodness problems in it. So here we go. I should probably not erase any of these things. I will regret, oh, there's another board, yeah. Okay, so one point I should make before I leave here, and put this thing down actually, is, the proof that we'll look at here in just a second for these, actually I will force myself not to look at the proofs because you guys would benefit more from me talking about subspaces, so I will forego my natural inclination to go over these boring proofs. I'm sorry, interesting proofs. But the thing is, by proving that these things are true from the axioms, right? And checking that all of these examples satisfy the axioms, right? We've automatically proved the assertion 1, 2, 3, and 4 for every one of those examples in the list, right? This in part is a lot of the reason that vector space, the idea of a vector space is interesting, is if we can make this abstraction, if we can identify that there's a common theme to all of these very different examples, right? And we can sort of boil it down to its core, which is this definition, then if we can prove things for a sort of arbitrary vector space, we've proved it not for one thing, but for all examples, right? And this is the big idea of abstraction. Well, it's one of the ideas of abstraction. That's not always how abstraction, abstraction is not always just an organizational scheme. Sometimes abstracting a problem, sometimes you can't solve a problem because you're too immersed in the details of the problem you're looking at, right? You have to kind of take a more general perspective, and then you learn that actually many of the things that were distracting you about the problem you're trying to solve were irrelevant. That's the kind of more interesting kind of abstraction where we replace a specific problem with a general class of problems which for some reason are easier to solve. Now that kind of abstraction doesn't happen so much in this course, all right? The kind of abstraction we do in this course is generally more sort of finding common themes, grouping things, and proving sort of theorems that are, well, kind of obvious a lot of the time. But I do think we get to some theorems later in the course which are a little bit less of a snooze fest. But yeah, start somewhere, right? And you're like, well, I may say that they're boring, but that doesn't change the fact that you guys have a hard time proving them. Let's see here. I mean, it's picky, right? It's picky. So here was the theorem. The proofs are like just hand-to-hand combat with the axioms. It's really different than almost anything else I do in this course. So I'm gonna go past this point here. When I will say this. When I put a question about the proof of the theorem I just covered up on the next test, if that's on the next test, I will reproduce the definition with the numbered axioms, because that's the only earthly way I can grade it, is if you also have the numbered axioms and can refer to them. I do not expect you to memorize the numbering of the axioms. I expect you to memorize the content of this, but if you were to reorder the list of facts, I wouldn't care, okay? All right, subspaces, definition. What is a subspace? V be a vector space over field F. W is a subset of V, right? Then that is, if that subset is also a vector space with respect to the inherited operations from V, restricted to W, then that makes W into what's called a subspace. In other words, a subspace is just a subset which is naturally a vector space on its own. All right. So a stupid example of a subspace would be V is a subset of itself, right? And V is a vector space if V is a vector space, so V is a subspace of a vector space V. Yay. Another less improper example, but equally trivial, although now in the technical sense, would be the set just containing 0. You can run through the axioms for a vector space. These are satisfied by the set just containing 0, which means 0 on its lonesome, the singleton set, is a vector space with respect to the vector space structure of V, which means that the set just containing 0 is a subspace rather of V. The notation that I'm going to use in this class is less than or equal to W. So watch out for this, okay? W subset of V in this class means subset. W less than or equal to V means W is subspace of V, okay? So these are, caution. Easy to miss this if you're not paying attention. All right. So I have a couple of examples here. And those examples motivate this next thing here, which is the subspace test. All right? Subspace test, what does it say? It says V a vector space over field F, W is a subset of V. If W is non-empty, then W is a subspace of V if and only if the following two conditions hold true. This is the so-called subspace test theorem. All right? So really, if you look at it, number one, well, it's not number one, it's number 0, right? Number 0, W is non-empty, right? Number 1, it's closed under addition. And number 2, it's closed under scalar multiplication. So C in F and X in W implies Cx is in W. So this is the subspace test theorem. If we have these three things, is it really three things though? What's the first thing we need? It's kind of, I just rolled it into the precondition in my writing on the board here. I need that W is a subset of V. I often forget to even comment about this because for typical problems, it's so stupidly obvious that W is a subset of V, it doesn't seem like it needs comment, but technically speaking, to be fussy, we do need that W is a subset of V. And there are contexts where that's something that needs to be shown. Not usually though, usually it's just there. On the other hand, 0, 1, and 2, you need to check all of these, right, for a proper proof of something being a subspace. Yeah.
I'm not sure if I understand the difference between a subset and a subspace.
Let's look at examples. I'll get back to that. The main reason I have this open is just for you to just kind of glance at this. To prove this theorem, it really is nothing more than running through the axioms for a subset and showing that if you're working in the context where it's the restriction of the operation and you have closure of addition and closure of scalar multiplication, that's really all you need because the commutativity, the associativity, the way that one multiplies, all of those other details transfer through automatically in the context of the subspace theorem. So the proof of the subspace test theorem is really, I mean, I could write this out, and in past semesters I even have done that, but at the end of it, I'm like, why did I do that? You know, it didn't give the students anything. So let's try to work on something that gives you guys something. So Dylan's question was a good one. How could a subset not be a subspace? All right, so let's look at an example. Well, non-example. One. It's my first non-example for today. So let's let V. How about 2 by 2 real matrices? That's kind of a fun example. And let's let W equal to the set containing, how about, I don't know, how about just the identity matrix? Yeah? And you guys give me any matrix you like. 1, 2, 3, 4. 1, 2, 3, 4 was the correct answer. Thank you. Why is this not, I mean, clearly W is a subset of our 2 by 2, right? Is it a subspace? That's right. So to disprove something being a subspace, since the definition is what? A subspace is a vector space in its own right with respect to the ambient operations that are there. So if it fails any one of the axioms, game over. And that's one of the reasons that you need to have the definition memorized. The numbering doesn't matter, but you do need to have those things, you know. So yeah, minus 1, 2, 3, 4 is equal to minus 1, minus 2, minus 3, minus 4. That is not an element of W, right? Therefore, axiom 4 fails. Therefore, W is not a subspace of R2 by 2. Okay? Non-example 2. Popular example, popular non-example, like the upper quarter plane. This would be the Cartesian product of 0, infinity with 0, infinity. If I put it in set builder notation, this guy is xy such that x greater than or equal to 0, y greater than or equal to 0. This has many nice features. It is closed under vector addition. You take the sum of two vectors in there, you're still in there, right? Like at this guy, like at that guy. It gets you to this guy, right? So forth and so on. Zero's in there, right? Zero's an element of W. Yay. Right. Clearly W is a subset of what? R2. So which axiom fails? How about this? Yeah, I mean, it's axiom 4 again. So axiom 4, let's see here. If you look at 1, 1, this is an element of W, but minus 1 is not an element of W, right? When you're showing when you're showing a counterexample, it's important to be specific, right? So that's a specific counterexample. There you go. Likewise, you could just, if we had like minus 2 times 1, 1 is equal to minus 2, which is not an element of W, right? So in this example, one of the subspace test rules, by the way, I have neglected an important F here, because this is if and only if. So if any of these doesn't happen, then you're out of luck. If W is empty, not a subspace. And we just showed that axiom part 2 of the subspace test theorem fails here. All right. Okay. Enough non-examples. Let's do an example. So let's let W equal to A in R2 by 2 such that A11 plus 2 times A22 equal to 0. Is this a subset of R2 by 2? All right, so we got that done. Notice A equals to 0 has A11 plus 2A22 equal to 0 plus 2 times 0, which is 0. Therefore, 0 is an element of W, which of course then is non-empty. So this is typically what's done. Look to see if 0's in the set. It's usually pretty easy to check if 0's in your alleged subspace. And if it's not, what's the added benefit of this? If there's no 0 in the subspace, do you need to look further at it? No, that subspace is not really a subspace. If 0's not in there, game over, not a subspace. If it is, you've proved it's non-empty. Great. What's next? We should let A and B be elements of W. and consider, we have to consider the test, right? Not that you guys would know, but at a typical club, there's like a bouncer, right? In order to get into the club, you must wear an appropriate kind of dress, or have your hand stamped at with the appropriately cool people. I mean, whatever it takes. I don't know. There's some sort of rule for entering the club. So to enter the W club, you must meet this condition, right? If you do not meet this condition, you cannot be part of the club, right? It's I mean, I'm not talking about that kind of club. I mean, like, replace this analogy with your favorite unnecessarily funded student club that your student fees pay for. Let's see here. So you need A plus B, 1, 1. Does that make it better? Let's see here, 2 times, I guess that makes it worse. A plus B. Did I guys tell you what I would do if I was elected student? Because my electronics professor was trying to get me to run for student body president at the community college when I was starting out. James, you should run for a student body president. It'd be a good experience. I'm like, but if I did get elected, if people were so foolish as to vote for me, my first act as the student body president would be to dissolve the student body and to reduce student fees, is to stop wasting people's money with these unnecessary things that are special to special groups. If people want to have a club, let them pay for it themselves. Stop increasing my student fees unnecessarily. Thank you. So anyway, A11 plus 2A22 plus B11 plus 2B22. Needless to say, I did not run. But it would have been funny if I did. My favorite story about student body president happened when I think I was in grad school at NC State. They failed to put into the bylaws that you had to run under your real name. So a guy ran as the pirate captain. Literally as the pirate captain. And oh, he won. He won big. And he went to every single student government association thing in full pirate garb, and would only speak in like "yar" and stuff like. It was awesome. It was awesome. Yeah, that was amazing. So as you can see, A plus B has met the condition to be in the club, and so therefore, A plus B is an element of W. Also, if C is a real number, then if we look at CA 11 plus 2 times CA 22, that's C times A11 plus 2A22, which is equal to C times 0, which is equal to 0. Therefore, CA, I'll get out of the way here in a second, is in W. Therefore, punchline, by subspace test theorem, W is a subspace of R2 by 2. Most interesting examples of vector spaces are constructed in this way, as a subspace of some sort of ambient vector space, which we already know is a vector space because somebody told you in a lecture, hey, this is a list of vector spaces. What does that mean? Actually, the real reason you should appreciate my 1 through 9 is that by saying those are vector spaces, I freed you from the task of proving those are vector spaces. You don't want to, I mean, nobody wants to write all that out, but it's clear that they are. So anyway, we will pick up again here next time. Oh, top hat. Oh, you made me say the words. How dare you. 9114. And you can go ahead and hit the, oh, never mind. I have your homeworks for you guys. I'll try to hand those out speedily after I kill this.